Hello everyone, and welcome to our ICCV 2025 presentation. This work introduces our paper titled Task Vector Quantization for Memory Efficient Model Merging, also known as TVQ. Model merging holds immense potential. By consolidating multiple expert models into a single one, it enables the performance of diverse tasks for the inference cost of a single model, eliminating the need to run multiple models in parallel, like an ensemble. In particular, the advent of the task vector concept, which represents the difference between a fine-tuned model and its pre-trained counterpart, has made it significantly easier to perform multiple tasks simultaneously through model merging. However, a significant and very practical barrier stands in the way of this vision: the massive wall of storage cost. For example, a single fine-tuned checkpoint of a VIT large model is approximately 1.14 GB. To merge just 20 different tasks, you would need 22.8 GB of storage. This amount is prohibitive for edge devices like the NVIDIA Jetson Nano, which may only have 16 GB of total storage. Ultimately, this enormous memory overhead has been a critical bottleneck, hindering the scalability of model merging. The most straightforward approach is to directly quantize the fine-tuned checkpoints themselves. We experimented with the latest model merging methods and observed a significant performance drop in an int4 environment. Fundamentally, quantization error is proportional to the dynamic range of the values. The wider this range, the more error will be incurred when compressing to the same bit width. The weights of a fine-tuned model exhibit a particularly large dynamic range. Consequently, quantizing them to a low precision leads to a catastrophic degradation in performance. Here we arrive at the most critical observation of our research. As you can see in the figure, the weight distribution of the task vector has a significantly narrower dynamic range than the weights of the full fine-tuned model. This is the key. A narrower range means lower quantization error. This led us to ask a fundamental question: what if we change what we compress? So instead of focusing on the entire model, we concentrated on the learned change. This is our core idea: to apply quantization not to the full model, but directly to the task vector, the difference between the pre-trained and the fine-tuned models. At the same bit width, our proposed TVQ achieves a lower quantization error compared to the conventional method of fine-tuned quantization. This allowed us to preserve the original model's performance almost perfectly, even at a low precision of 3 bits. However, even TVQ showed a relatively high quantization error and performance degradation in the extreme environment of 2-bit quantization. To conquer this ultra-low bit regime, we introduce our second innovation, RTVQ residual task vector quantization. First, we calculate the central direction of change that is common across all tasks, which we call the shared base vector. This is defined as the difference between the average of all the fine-tuned checkpoints and the original pre-trained model. Next, for each task, we calculate a small residual, the offset vector, which represents how much it deviates from this common quantized base vector. We implemented an error correction mechanism. The error generated from quantizing the base vector is corrected for when calculating the offset vectors, minimizing cumulative error. We assign high-precision 3-bit to the base vector, which is stored only once. Then we assign low-precision 2-bit to the multiple, but much smaller, offset vectors. As a result, we achieved remarkable performance resilience, all while using an effective rate of just 2.x bits per task. In merging 8 classification tasks using VIT-B32 and VIT-L14 models, the results were clear. Full checkpoint quantization FQ completely failed at 4 bits. Our initial TVQ showed significant performance degradation at 2 bits. However, our RTVQ, despite using an even lower effective rate of 2.375 bits, delivered accuracy that was on par with, or even surpassed, the original FP32 performance. We then tested scalability by increasing the number of tasks to 8, 14, and then 20. As you can see, the efficiency of RTVQ, its performance per bit, actually improves as the number of tasks grows. It consistently maintains stable performance even in extreme low-bit environments. This success extends beyond image classification to dense prediction tasks like segmentation, depth estimation, and normal estimation. You can observe here that the object boundaries, which are blurred and distorted with 2-bit TVQ, remain sharp and clear with our RTVQ. This raises an interesting question. How can performance be maintained or even improved after compressing the information? We analyzed the cause from three perspectives. First, improved cross-task generalization. Extreme quantization forces the model to discard some task-specific information and instead learn more general features that are useful across multiple tasks. As a result, while performance on the original target task might decrease slightly, performance on other tasks improves significantly. Our RTVQ method finds the optimal balance between these two. Second, the regularization effect. Quantization is analogous to adding noise to the weights, which prevents the model from overfitting to the training data. In fact, our experiments confirmed that the quantized task vectors often achieved higher test accuracy than the original uncompressed vectors. Third, the implicit pruning effect. Task vectors contain many values that are close to zero. During the quantization process, these small values are mapped to exactly zero. This has the effect of pruning unnecessary parameters, making the model sparser and more efficient. In summary, to solve the storage cost issue, a critical bottleneck in model merging, we proposed two powerful quantization techniques, TVQ and RTVQ. Our method achieves up to 92% in storage savings while maintaining performance that is on par with, or even better than, the original models. It also integrates seamlessly with any existing merging framework without modification. Now, developers can build powerful and efficient AI by combining the knowledge of more models, more freely, without worrying about memory constraints. We hope our research serves as a cornerstone for a new collaborative ecosystem in AI model development. This is our project page. If you have any questions, you can contact us by email. Thank you for your attention.